Hello.
Hi.
Hi, good morning, sir.
Hi.
My
Morning.
voice is audible to
Good
you.
morning, good morning.
Morning.
Just
Morning.
wait
Hi,
one, two
Rajat.
minutes more. Uh,
Good morning, sir.
uh,
Good morning, guys.
Good morning to Pawandeep Singh ji.
Good morning, Sanjeev
Hi.
ji.
Good morning,
Uh,
HRP,
all
sir.
well?
Good morning.
Shall I start
Uh,
the event?
Yes, yes.
Or okay, thank you very much, sir. Good morning to all respected dignitaries, our distinguished speaker, faculty member, and dear student. On behalf of Amity University, Haryana, I extend a very warm and heartfelt welcome to all of you for this international online expert talk on artificial muscle and soft robotics. Amity University, Haryana is a leading and multidisciplinary university dedicated to quality education, cutting edge research, innovation driven learning. The university offers a wide spectrum of programs in engineering, management, applied sciences, and many other contemporary domains, catering to the need of modern world. Our campus provide a vibrant, student-centric, and research-oriented environment. We are equipped with the state-of-the-art laboratories, modern smart classroom, advanced computing, and well-stocked central library, innovation and incubation center, and strong linkage with the industry and research organization. The FSS is not only academic excellence, but also on skill development, innovation, ethics, and values, so that our students emerge a competitive, professional, and responsible global citizens. The Amity School of Engineering and Technology is actively engaged in promoting interdisciplinary learning and research. The department regularly organizes expert talk, workshop, industrial visit, and conferences to bridge the gap between the classroom learning and real-world applications. In line with this vision, today expert talk on artificial muscle and soft robotic focus on the one of the most promising and rapidly evolving area of the modern engineering. Artificial muscles and soft robotic systems are playing a crucial role in next generation robotic biomedical devices, assistive technology, and wearable systems and advanced manufacturing. By integrate concept from mechanical engineering, material science, electronic, and artificial intelligence, this field offers immense potential for innovation, entrepreneurship, and high impact research. Sessions like these provide our student faculty with an opportunity to interact with the leading experts, gain insight into global research trends, explore new ideas, and get inspired to take up innovative projects and higher study in such emerging domains. We are truly honored to have a distinguished speaker with us today. We look forward and engaging, insightful, enriching session. Thank you very much for once again a warm welcome to everyone joining us for this expert talk. Now, I humbly invite Professor Dr. H.R.P. Yadav, in absence of our Director Sir, to say a few words. Director Sir is busy in some preoccupied task. Now, I invite to Professor Dr. H.R.P. Yadav.
Thank you, Dr. Hardyal Singh ji. Good morning to our
Thank you, sir.
expert speaker, Dr. Pavandeep Singh Matharu ji, my colleague, Head of the
thank you.
Department, Mechanical Engineering Department, Dr. Sanjeev Sharma ji, and my colleagues, Dr. Ravi Kant Sharma, faculty of the Amity School of Engineering Technology, Mechanical Engineering Department, Dr. Hardyal Singh, and many distinguished colleagues, participants, delegates, dear students, ladies and gentlemen. As my colleague Dr. Hardyal Singh has elaborated that this prestigious university, Amity University, Haryana, Gurugram, has adequate infrastructure, facilities of imparting higher education in excellence manner, state-of-the-art laboratories, quality faculties, various departments dealing with engineering technology. We have created milestones by establishing research innovations, filing of patents, its publication and grants, research publication in Scopus journals, high impact factor, H index, I index, etc. Today, the mechanical engineering department has organized an expert talk to be delivered by the esteemed speaker, who is none other than Dr. Pavan Deep Singh Matharu. He is an expert of artificial muscles and soft robotics, having doctorate from Texas, and his expertise is to deal with the artificial muscles and soft robotics, which has got tremendous applications in modern age. I will not take much time. I would simply say that this expert talk or lecture by Dr. Pavandeep Singh Matharu will certainly benefit the faculties and students of ASSET in particular and the students of AUH in general. My colleagues, Dr. Sanjeev Sharma, Dr. Ravi Kant Sharma, Dr. Hardyal Singh, Dr. Rajesh Arora, Dr. Narendra Kumar, they all are esteemed faculties of the Mechanical Engineering Department, deserve congratulations and appreciation to organize such expert talk for the benefit of the students. I hope that Dr. Pavandeep Singh ji, with his illuminating talk, will certainly emphasize some of the research and development activities in this area, that is artificial muscles. The literal meaning of the word artificial is very much compact, and nowadays, like artificial intelligence, artificial muscles, these all are playing important role in understanding the research and innovations by minimizing the use of manpower and infrastructures. That's why technology has evolved such type of techniques which certainly reduce the involvement of manpower and increase the efficiency of the process and system. So with these, I welcome heartily to our guest speaker, Dr. Pavandeep Singh Matharuji, to deliver
Thank
his
you.
expert talk on this momentous occasion. Thank you very much, and I welcome you once again, and I hope your
Thanks a
talk
lot.
will
Thank you.
certainly give us a great insight on the topic as selected by our mechanical engineering department. Thank you once again.
Thanks
Welcome
a
you
lot,
once
sir.
again. Thank you.
Thanks a lot,
Thank
sir.
you very much, sir.
Uh,
Just
oh,
wait, sir.
okay. Sure, sure, of course.
Thank you very much, sir, for your kind and motivating words. Now, I kindly invite our head of the department, mechanical engineering, to say a few words.
Yeah.
Thank you, Hardyal sir, for arranging and organizing all these things. Thank you, ex-director sir, HR Yadav, head of the Department of Civil Engineering. Thank you, Ravi Sharma ji. He is also very much involved in this whole activities. So, in this regard, first of all, good morning to all. On behalf of Department of Mechanical Engineering, Amity School of Engineering and Technology, I extended my warm welcome to everyone present for the today's international online experts talk on artificial muscles and soft robotics. It is my honor and privilege to welcome our distinguished guest, Dr. Pavandeep Singh Matharuji. He is a research scientist in Department of Mechanical Engineering, Wayne State University, an extended expert, an eminent expert in the field of soft robotics and advanced smart materials. We are grateful that you have accepted our invitation and joined us today to share your deep knowledge and cutting edge insight on this rapidly evolving domain. Your presence adds the immense value of this academic gathering. Artificial muscles and soft robotics represents the future of intelligent machine offering flexibility, adaptability, and the human-like motion. As a researcher and the students of engineering, we are fortunate to learn from a global expert who is working in shaping the next generation of the robotics system. I also extended my warm welcome to all faculty members, researchers, HOIs, HODs, staff, and dear students who have joined us to participate, make this event meaningful and enriching. I sincerely hope that today's session is inspire collaborative thinking, new research ideas, and innovative approach for the future project within our department. Once again, I welcome you all and look forward for insightful and engaging talk. Thank you very much.
Thank you very much, Dr. Sanjeev Sharma, sir, for your encouraging words. Uh, Now I have pleasure to introduce Dr. Pawan Singh Mathadu. Dr. Pawan Singh Mathadu is a research scientist in mechanical engineering at a Vienna State University specializing in soft robotic, artificial muscle and bio-inspired system. He earned his PhD from University of Texas at Dallas, where he developed high-performance electrothermal actuators and morphing soft robotic structures. His research integrates material science, mechanical design, and control to create adaptive robotic platforms with embedded sensing. Dr. Matharu has contributed to major projects supported by Toyota Motor Corporation, Toyota Research Institute North America, and the Office of the Novel Research. He has published in leading journals including Smart Materials and Structures, Nature Portfolio, Ocean Engineering, and ESME, and holds several patents in artificial muscle and bio-inspired robotic with Toyota North America. He also served as a reviewer for scientific reports, Ocean Engineering, and IEEE. His current work focuses on scalable humanoid and underwater robot using TCP, TCP-FL actuator, SMA, soft sensor, and hybrid additive manufacturing. Now I hand over the session Dr. Pawan Singh Mathadu.
Hello. Hi.
Hello.
Uh,
Hi.
Hi guys. So firstly, thank you. Thank you for the lovely words and morning to all of you, to all the faculty and students.
Good morning.
So good morning. So as has been explained and spoken by all the faculty so far, uh, I will be speaking on a broad topic of soft robotics. And as you all know, or might have heard, soft robotics is definitely one of the most upcoming and new streams of robotics, which is actually being used by uh, various defense forces currently to actually make their defenses stronger. And especially for me, working on various projects for the US Navy over the past 5 to 6 years, I can definitely say that uh, even our armed forces are currently trying to work in these areas. So whichever faculty back in India and whichever students uh, would like to do uh, something good, probably my slides will be there as a base for you all maybe. So thank you again. Uh, Before I start to talk, let me share my screen and my slides. So maybe Dr. Singh can let me know whether you are able to see my slides or not. Are you able to see my slides?
Yes, sir. Yes, it is visible. Yeah.
Okay. Okay. Uh, Let me go to the full screen mode, right? And then I can start.
Yes.
Okay, just give me a second, please. Okay. Uh,
Yes,
so
now
like
it's clear. Yeah.
so it's there, right? Visible.
Yes. Yes.
All right. Okay. All right. So let's begin, guys. So firstly, good morning, good evening, to all. Uh, as you all know, I will be today giving a talk on the topic of novel artificial muscles with applications in bio-inspired soft robots and robotics as a whole. Currently, I am working as a research scientist in the Department of Mechanical Engineering at Wayne State University. I will be soon joining University of Michigan, where I will be continuing my current portfolio as research scientist, but I will be also giving lectures in various courses from next spring. So that is my new base starting from January. Uh, as can be seen in the screen, yes, even I have completed my PhD. That was last year. So I completed my PhD from the University of Texas at Dallas. Currently, these are the number of patents papers I have. So my core research interests are artificial muscles, soft robotics and smart materials, humanoid robots, underwater robotics, advanced manufacturing, and soft sensors. So, as you all know, currently most of the robots that you might have seen, they are highly programmable, while they are predictable in terms of force, speed, and they are repeatable for millions of steps, like we see in various plants, right? When we try to like assemble different parts of cars, these are the robots that are used in various places. These robots can be confined in one area, but they can only perform single tasks. They are not programmed, or they are not made to do multiple tasks. So this is one of the drawbacks of these robots. Plus, there are some safety issues with these robots also. Uh, but we do want so over the years, researchers all over the world, they have now tried to mimic or try to provide that intelligence to these robots, which can adapt to daily changes, uh, like us, to give some brains to these robots like we have. But that is a humongous task, and it needs years of work still. However, if we work on the structures of these rigid machines, we can make them reconfigurable, adaptable, and we can make them safe. Now, how we can do it? We can try to mimic real animals like these fishes in water. Uh, so which have a structure which is soft in nature, which is not rigid. It can be safe, and it can change its shape and size according to the surroundings or place where it is. Now, if I go to this graph, I will basically, right now the robots are rigid, or most of the robots currently are rigid in structure. They have a limited number of degrees of freedom. Uh, Most of these robots have 3 to 6 degrees of freedom. But in order to do precise tasks like this, you need something or some grippers which are not rigid, and something like human human palm or human hand. And some of the tasks which require less forces, for that, we might need structures which are soft in nature. So for that reason, we want to develop biomimetic soft robots, and we especially do not want to use motors and pumps. So uh, when we use motors and pumps, the robot is no uh, is not soft. Basically, it is still rigid. because the motors are heavy and the pumps are also loud and heavy. So we do want to develop something which is called artificial muscles. This is the current research expertise which I have or I am working on. So let's go through each one of them. So firstly, it's about development and understanding the behavior of artificial muscles. So this is so before we start to make these complex robots and these maneuvers, we want a repeatable artificial muscle which can sustain millions of life cycles, like the one which is shown in this video and in these figures. Uh, this muscle is called a TCP muscle, or a twisted and coiled polymer muscle. This research is pretty new, and even in the US, uh, I am lucky, or I have been lucky to work with Dr. Ray Bauman, who who is a pioneer in the field of muscles all over the world. So I have been lucky enough to work with him, and we are one of the few labs in the world who have developed these twisted and coiled polymer muscles, which can be used to develop various robots. Secondly, I have, as I mentioned earlier, that the US Navy is currently trying to mimic various animals like the one shown here. This is a jellyfish, and I have been working on various projects to develop 3D printed jellyfish robots or soft jellyfish robots with the help, or which are actuated with the help of these artificial muscles which are shown here. Similarly, uh, currently, big automobile companies are trying to make or trying to include some soft robotic features in their vehicles, and hopefully you will be able to probably see some of those soft actuators or artificial muscles or soft structures in certain Toyota vehicles in the next few years. Definitely, this is one of the projects. It's a soft morphing structure actuated actuated with these soft muscles. And finally, I have a soft morphing structure in terms of humanoid robot, which is also one of the projects that I am currently working on. Moving on. Okay. Okay, I think my screen has hung. Just give me a second because my screen has hung because of the videos. Hello?
Yes, sir. Yes, sir.
Yeah, yeah. Just give me a second because I think my slide
Yes, sir. No, sir. No
was
problem.
having
Yes.
too many videos, I think. Just give me a second. Mm, yeah. Okay. So I will skip that slide because that is a very heavy slide. Uh, okay. Okay, I'm sharing my screen again. I'm very sorry. Uh, are you able to see my slides again?
Yes, it's visible.
Hello?
Yes, it's visible.
Okay, great. So currently, if we see the broad field of biomimetic soft robotics, these are the four different research areas, or the areas which are currently being worked upon. That is softness. Your structure has to be flexible and it has to stretch. We don't have any rigid components in these robots. Next is, as I mentioned, actuation, conventional and non-conventional. With conventional actuation, we mean actuation with air or water, as in pumps, and with respect to motors, and non-conventional, which mean the new type of muscles or the artificial muscles, which are being developed in the field of smart materials. Next is working on the electronic side of things. So to actually make these robots autonomous, we have to have sensing capabilities, and the robots can be controlled, or their movement in terms of position and speed has to be also controlled. And finally, the amount of power that, so let's suppose the work shown here for the walking robot by Drotman et al. This is using CO2 gas. So this is basically wireless, and it can go through various different structures and paths. So this is the fourth research area that is currently being worked upon in the broad field of soft robotics. Now, what is the major objective or the axis of robotic design? We have to understand the behavior of non-conventional actuators under harsh conditions. So not only in air, but these actuators should work in air, space, and water. So we need soft actuators or artificial muscles, which can be used in all the three broad domains. Next is designing and manufacturing of self-contained underwater soft robots. So as we all know, I think maximum of the oceans are, like, I won't be able to give you a certain number, but maximum percentage of oceans are like rigid robots cannot go there basically. So because of the high pressure of the depth. So as we go inside water, uh, I believe all of you would have learned in the field of fluid mechanics that equation of rho g h. So as our h will be bigger, our pressure will be more. So the rigid robots, or a body which is having a rigid structure, as it goes down, say this robot is a rigid robot, as it goes down into the ocean, more height or more depth added to the robot, the structure will get damaged due to the high value of pressure, or P. So for that reason, we need structures which are soft in nature, and which can go to various depths of the ocean in order to explore and know what really is there within the ocean and seas. Third is to test all these robots to perform tasks such as surveillance and to also transport, to probably go from one place to another by staying down at very high depths inside water. And finally, to understand the actuator performance through modeling and experiment. So theoretical modeling is a very important part in whatever research we do, because that sets the base for whatever machines or robots which are being created. So we have to first know and understand the physics of these soft robots, and from then on we can start to apply our engineering skills to actually manufacture and fabricate these robots. Now, as I mentioned earlier, uh, soft robots have high degree of freedoms. Uh, it has infinite degree of freedom, because they do not move in a certain direction only, like the conventional or the rigid robots we have right now. They have to be robust, and they should have the potential to exhibit agility, sensitivity, and unprecedented adaptability. Now, to successfully develop a soft robot, we first have to begin from the basic, which is the actuator. So we have to first manufacture or make something which can help that soft robot to move in nature. So we have to first go towards the science of making an actuator. We know that conventional motors are energy efficient. They can be easily controlled, but they are bulky and expensive. Plus, we know that pneumatic actuators are repeatable, but even they are bulky sometimes, and they actually are expensive, and they can produce loud noise. So the main goal of these smart artificial muscles should be they can be easily fabricable, they can be scalable in the sense that for different applications, big or small, our actuator can we can fabricate a actuator which can be big or small also. They should be quiet in operation and lightweight. They should have various load carrying capacities. They should be fast because for various applications we require fast actuators. Say for an application which requires us to replace a motor, we need a similar sort of artificial muscle which can actually replace a motor and be as fast as a motor. Similarly, it should have low power requirements, and the life cycle of these artificial muscles should be very high, uh, in the range of millions of cycles. If we are able to develop these artificial muscles, they can easily replace conventional motors and pumps to then create soft robots, which have to be mass manufacturable, should have a control geometry. Now, with control geometry, I mean to say that whatever feature we want to mimic of a certain animal, we can easily mimic it by just controlling a CAD design. Thirdly, we can actuate it with these artificial muscles, and they should also have reduced power requirements and the fast actuation. Now, let's begin with the broad field of smart materials. Now, smart materials are a field of class of materials that are responsive to multiple stimuli uh, and have coupling between different domains. So, as you can see in this figure, I have I basically drawn a figure which shows that mechanical impulse can be formed or can be a result of an like an electrical current or voltage provided to some material like a piezoelectric material, and similarly a thermal effect to a shape memory alloy can provide a mechanical impulse. Now, these are the various smart materials in nature. There are more smart materials, but the five major smart materials are twisted and coiled linear actuators, which are shown in this GIF, piezoelectric composites, which are these shape memory alloys, which can change their shape with the change of heat in the like shown in the GIF again. Thirdly, right now we are working on dielectric elastomers or DEAs, and finally IPMCs or ionic metal composites. Now, no one can work on all the things, but we have to specialize or work in certain domains or research areas. So two smart materials which I currently am working on, and I've based my PhD work on, are twisted and coiled linear actuators and shape memory alloys. Now, what are artificial muscles? Artificial muscles are actuators which contract in response to change of environment. So, as can be seen in this figure, this is a simple way to fabricate a TCP fishing line. So so we just need a polymer fiber which can be attached from one end with a motor, and on the other end with a weight. Once we start to twist the motor, the polymer fiber will start to coil like this. And once we provide that tension within this polymer fiber or a coiled fiber, it will it will again start. Once it finishes the coiling, it will start to form twists. And once we form the twist, we just get our TCP muscle like this. Now, when we provide heating to this same polymer fiber, it will move up or shrink. And when it is cooled down, it will go back to its original position. So this is the simple movement of this artificial muscle. Uh, it is somewhere close to a muscle fiber of uh, of the muscles which we have. So we are trying to mimic the human muscles by developing these sort of muscles. Now, when we move on to this graph, currently we see that if we compare in terms of strain and stress for these TCP muscles, they are compared to other major artificial muscles, and they are now coming closer in terms of strain per stress with the servo motors which are being used. So the research is still going on. We are still trying to make these muscles better. But yes, it is reaching the point where we can actively start to sell these muscles. Now, as I explained in the previous slide, this is just a polymer fiber or a simple fishing line. So a fishing line, I think most of you in videos would have seen people going to fish in some lake or a pond. So this is that same fishing line which we use to actually fabricate these muscles. These are very cheap in terms of cost and price, I will say. Hence the sellability factor of these muscles becomes very high because the costing or the cost price of these muscles is very less. They provide compact shape, they are scalable, they are strong, and yes, as I mentioned, they are very less in terms of cost. These are the various steps. I think whichever student wants to do their research in this field, I think they can go through my papers maybe. But this is a figure showing the experimental setup which can be used to fabricate these muscles. So it just requires some stepper motors, uh, three motors, I will say, and then just simple wooden planks to actually make this whole thing. So in terms of the cost price and everything, this is one of the cheapest artificial muscles going around currently. And yes, as I told you, if you just apply voltage to it, that will heat the wire which is coiled around the fishing line, and that will allow the fishing line muscle to shrink and then expand, like shown in this video. So as can be seen, I will just speed it up. Okay, I think again my video. Yeah, because of the videos, I think PowerPoint is hanging. I'm really sorry, okay, because of the videos, the slides are getting hang.
No problem.
So hopefully this will. Okay, uh, sharing back. Are you able to see my slides, Dr. Singh?
Yes, sir. Yes, sir. Yes. Yes, sir.
Okay.
Yes, sir.
Okay. So hopefully my video will play without hanging. So uh, this is a this is a novel muscle. So currently we have just submitted this paper in Nature. So hopefully this will be accepted there and we will have it published. But I have named this Blackie TCP because of its color. Now, what is happening is that I have coated this muscle with nanomaterial coating. So I've used graphene powder to coat these muscles or the fishing lines, and with the help of the thermal conductivity of the nanomaterials, the overall performance of this muscle has enhanced than a conventional non-coated TCP muscle. Now, probably in my future slides, I will have more on it, but this is how this muscle works. Okay. So the major highlights of these TCP muscles or twisted and coiled polymer muscles is that the traditional TCPs in terms of life cycles were giving 10 to the power of 3 cycles only. So it was close to 1000 or 2000 cycles. So this is a logarithmic scale. Hence, this is in the range of 10 to the power of 3. So when I wanted to develop a better twist and coil polymer muscle, I coated it with multi-wall CNT and graphene, and that enhanced the performance and life cycle of these muscles to now close to 10 to the power of 5 and inching on to 1 million cycles, which in turn will reach somewhere where a normal motor works. So a normal motor or a pump is expected to work at least for 1 million cycles. So that is where our aim is. This is where we are. So the muscles in our body are somewhere here, 10 to the power of 9 cycles. So, but the current artificial muscles are somewhere in the range of 10 to the power of 6. So we definitely want to go further and reach somewhere close to the muscles which we have. And definitely in terms of strain, the Blackie TCP which I have developed recently, this is improving, but still there is a lot more improvement to be done in terms of the actuation strain. But yeah, this is where currently we are in terms of the TCP muscles. Now, let's move on to the second research area. So, as we all know, there are many agencies, even I think back in India, the Navy, Coast Guard, and various agencies want to actually keep our shores safe. Plus, we do want to also explore whether we have various minerals in the seabed that we have in the Arabian Sea, um, the Bay of Bengal, and the oceans which actually are there. So for that reason, the marine research becomes a very important part in the growth of our nation, as well as to keep our nation safe. And that is where the research in the domain of underwater soft robots comes into play. So my second research expertise, so to speak, is in the design and development of soft bio-inspired underwater robots actuated with noiseless artificial muscles. Now, you would definitely ask me that there are so many animals inside water, but then why am I choosing jellyfish? So jellyfish are known to have one of the highest energy efficiencies amongst all the animal swimmers. Plus, they possess, as you can see, the movement is very simple, right? They possess a limited set of structural components compared to all other muscle-powered animal swimmers, like we see here. So these are the best known underwater jellyfish soft robots thus far. There are more. I don't have the newer ones. I think I have until 2023, but I think I could have added one or two more. But these are the most well known. I think the one out here. This is my work. While this is my work also, but still we have a long way to go in terms of mimicking an actual jellyfish animal. It looks simple, but to actually mimic and portray a similar movement and energy efficiency as a jellyfish is very difficult on a robot. There are fundamental issues with these robots. Number one is that they are not mass manufacturable. So currently most of the robots, they either are molded or they are manually being developed. uh, 3D printing is one thing that is being used, but 3D printing is also slow. So we need a mechanism which can mass manufacture these robots. Secondly, we need to develop controlled geometry. So some of these robots, as you can see, they are they're trying to mimic a real jellyfish, but still it cannot cannot mimic a jellyfish, whoever it is. So for that, uh, we need to make a mechanism in which someone can design a CAD model which can directly be used to develop a controlled geometry for the enhanced robot performance. My God. I think my slides don't want to play today. Just I'm very sorry, guys.
No problem.
How many more slides
How
you
many
have,
more
Dr.
slides you
Singh?
have? So I was told that I need to give a talk of 1 hour.
Okay.
So I think I still have 15 more slides, maybe.
Okay. Good.
Uh, but yeah, I think most of the slides are videos only. So I will just quickly move on. Okay. Uh, so so in order to mimic a jellyfish, we need to mimic its movement, which is bending or flapping. So this is the sort of movement we wanted to mimic. Now, we do know that a jellyfish have all these muscles, and in terms of uh, arranging the muscle, we try to develop those TCP muscles and provide it the same placement as a real jellyfish. Now, this is one of the first robots that I developed with the help of the TCP muscles, which I showed, and this is the video. This is the video for it. So as you can see, this is me during the test, and I have a camera attached with this robot so that it can actually know whether someone is standing there or not, or something like that. So this is one of the projects that we did with the help of an AI powered camera. Uh, Certainly the underwater domain is quite huge. So there is a lot of work to be done. Now, this is the work or the project that was published in Ocean Engineering. This is I named this robot Sogel. So based on the undisturbed swimming, we try to mimic different shapes and forms of a jellyfish robot. And with the help of the shape memory alloys, we try to develop this robot. And currently the robot was wired, but right now we are now moving towards a non-wired or wireless robot, which can actually mimic a jellyfish in real terms. One more thing that we did is that this is one of the first 3D printed robots or 3D printed jellyfish robots. So this is a shape memory alloy coil. I think this is a very good research that can be done by the students, because this is a coil which can just change its shape with the help of heat, and this is the whole work basically in gist. Moving on, I developed a robot Jelly Z. This was published in Nature. This is published in 2023. This is also a jellyfish robot, but the artificial muscle and the shape of the muscle uh, and the shape of the robot is very simple compared to the last robot, as you can see here. This is just using the TCP muscle which were fabricated by me and my team itself, rather than buying them. So this is a fully customized robot, and we are trying to develop it more so that we can start to sell it maybe in future. Now, when we compare all the robots that have been developed to the real animals, the real jellyfish, the in terms of its energy efficiency is somewhere here, which is 1, while the robots are in the range of 10 to the power of 5. So there is still a long way to go in order to match a real jellyfish animal. So the research scope for all the students and faculties, I think, is a lot in this area. So this is one thing that we all can work towards. Now, Toyota Research Institute of North America, they sponsored my research on soft morphing skin structures. So what they wanted me to do is to develop a soft skin like the one you saw earlier, and they wanted me to make it fully soft so that there are no rigid components in the skin, so that they can use it inside their cars. So this is one of the single layered skins that I developed with the help of TCP muscle, and I use those skins to develop a soft gripper which can actually grip different objects and things. And this is a humanoid robot, and as you can see, it can pick and place different sized objects with the help of that soft skin. This work was published in Wiley Journal of Polymer Science last year. So this is definitely one of the new research areas that students can work on. Okay. Yeah. So these were the different objects that the robot was able to pick and place. Uh, I don't want to spend time on this because it's okay. So this is one of the research that I did when I was working back in India. This is back in IIT Kanpur. So I would like to show the students the video because it is having its own audio, and this is about the river, uh, and I think that the students will like it a lot. So just let me know whether you can hear the sound or not of the video also. Dr. Singh, are you able to? So are you able to hear the sound of the video?
No, sir. Sound is not there.
Okay,
It's not
now?
audible.
Sound is not coming.
Sorry?
Sound is not coming.
Okay, just give me a second, okay? Maybe I need to share the audio. Okay. Do you know like how to share the audio here in Zoom? Okay, I got it. Share sound. Okay. Okay, now?
Technology, Government of India.
Yes.
And
Now?
It's audible now.
Yes, audible.
All right, all right, all right. So I will have it full screen and played. So this is a five-minute video, but then I would urge all the students to see it. So here goes.
the story inside this truck is of a project being funded by the Department of Science and Technology, Government of India, and Intel, and administered by the Binational Indo-US Science and Technology Forum, or IUSSTF. The Aquatic Autonomous Observatory, product of the Indo-US Collaborative Project titled Design and Development of Aquatic Autonomous Observatory, Nirakara Swamsasita Vedjala, NSVS, for in situ monitoring, real-time data transmission, and web-based visualization, is being prepared to be anchored at the Bitur River in Kanpur. Designed, structurally analyzed, calibrated, and put together at the Smart Material Structures Laboratory at the Indian Institute of Technology at Kanpur. It sends real-time data every 30 seconds to the IIT Kanpur labs. This aquatic observatory works on its own through its onboard unique energy harvesting and communication systems.
Energy is the key element for us. If the power requirement is high, then we need large battery and the system would become expensive. Whatever energy we are harvesting from the ambience, from the sun, and also from the flow of the water, we want to power our sensors as well as our communication system with the help of that.
To power the sensors, there are solar harvesting systems.
Now the total amount of energy that can be generated in this system is around 28 to 32 watts. The solar panels which have been integrated here can generate approximately 18 watts.
This is the experimental setup that displays how the observatory derives its power from the vortex created by the water in the river or any aquatic system.
The vortex-induced vibration system, which has been integrated at the base, can generate around 5 watts.
The third system we have is for the locations where we get a good wind power.
And the vertical axis wind turbine, if it is integrated, can give up to 8 watt of energy.
The soul of the observatory are these sensors that keep feeding data on more than 70 water quality parameters.
We have 5 important sensors sitting inside the top cabin, and these are related to temperature, turbidity, acidity or the pH level, conductivity, and the dissolved oxygen that is there in the water. Indo-US partner Seoul Institute is playing a very important role in developing 2 types of sensors.
The channelized optical sensor, or CHANOS group of sensors, from the Wood Shoal Oceanographic Institute in the United States is exceptional because it needs very little power to function and behaves well in a robust environment. The data fed by sensors needs validation beforehand at the laboratory to assess how accurately they perform on location.
Particularly for this project, we are trying to measure a lot of heavy metals, like for example, chromium, which is a big problem in this field because of the tannery industry.
Measurement of chromium and copper with the spectrophotometric sensor are currently in progress.
Have to actually bring back the samples to the lab, and this, in the background, the instrument you see, it's called a mass spectrometer, this is the only installation in India that we have right now, which is funded through the IUSTF project.
Yet another crucial part of this aquatic observatory is its communication subsystem.
This is the communication subsystem, which is responsible for taking the data that is collected from the sensors and communicating it and transmitting it to the servers where it is stored safely.
And every 15 minutes, the readings coming in from the sensors can be visualized on the mobile phones. Once the data is obtained in large enough volumes, predictive models can be created on how pollution or various components of water quality will behave over time.
Are you ready to take your first step into the exciting world of space science and technology?
All right. So I think this is a project which is very close to my heart. You will find these observatories in various sections now, in various rivers back in India, especially the bigger rivers, because we wanted to monitor the quality of water. The first step to keeping our rivers safe and flowing and clean is to firstly know whether the water quality is good or bad. So this was a project that was sponsored by the IUSSTF, the Indo-US forum, and this was a buoy or a marine floating platform that was fabricated and developed by me and my team. Uh, One of the future works that probably all the faculties and students who like to who like that like this challenge is to develop a moving robot within these rivers which can go inside smaller streams, and because the the water which is actually making our rivers, the Ganga or the other bigger rivers, dirty are those smaller streams. So if we can somehow build those robots which can move inside those smaller streams and measure the water quality, I think that can be a very challenging but a very, very nice project to work on. So this is one of the work that I did. Uh, this is the last project or the work that I would like to show. So currently, the humanoid robots that that we have or we can see are either they can climb stairs and ladders, they can be adaptable to human environments, and though they look like us, but they are slow to reach their destinations. The movements are unstable, the payload capacity is low. While if we use wheeled robots or four-wheeled robots, the pros are they can be energy efficient, they can operate at faster speeds and at higher payload capacity, but they are not humanly friendly and they have poor obstacle navigation. So this is a US Navy sponsored project on which currently I'm working on. This is called a hybrid humanoid to quadruped robot, and this is a robot which can change its shape. It can go to its 2 feet or it can go to its four limbs whenever it wants to, so that it can navigate different paths, different structures whenever it wants. It can climb a stair, it can change into a feet, while when it wants to move fast on a flat floor, the feet can change into wheels. So this is where the knowledge of soft robotics comes, and this is something that currently I'm working on. I thank to all my collaborators, all my uh, all my friends, and yeah, this is all from my side for today. I again want to thank all the faculty members and especially Dr. Singh, who actually reached out to me. And yeah, that's it from my side. So
Okay,
thank you.
thank you very much, Pawandeep sir. Very insightful session where you have shown the very innovative work and presentation. Now we
Thank
will
you.
move to the question and answer. First question asked by one BTech artificial intelligence and machine learning student. For a
Okay.
beginner in this field, which sub area of smart material would you recommend focusing on for a project or minor research work?
Just,
Okay. Uh,
just Dr. Singh, before you just give the opportunity to the students, I will just say a few words to Dr. Pawandeep Singh Mathura ji, who has
Okay,
made a
definitely.
very fantastic presentation. He elaborated very lucidly about the applications of the these artificial muscles and framing this soft robotics in various ways. He has given the examples of various kinds of muscles, artificial muscles, and applications in the emerging technology for the benefit of the society. He has highlighted the use of soft robotics, which is the very emerging areas of research and innovation, and he has motivated us how to create innovations for the benefit of the society using the artificial muscles techniques and soft robots. With this, I once again congratulate Dr. Pawandeep Singh Mathuraji for his illustrious talk and very much motivating. And now question answer session starts. I hope the students will get benefit from his expertise by learning something about this coveted topic. Thank you very much, Dr.
thank you.
Pawandeep Singh, for sparing your valuable time and giving a very
Thanks a
fantastic
lot.
talk
Thank you.
for all of us. Thank you.
Okay.
Thanks a lot. Thanks a lot, Dr. Yadav. Thank you.
Thank you, sir. Now, first question from asked by the Bhumika. For a beginner in this field, which sub area of smart material would you recommend focusing on for a project or minor research work?
Okay. I think firstly the question is good. So I think you mentioned the student has a background in machine learning, right? Machine learning and AI.
Yes, sir. Yes.
Okay. So I think that the best way to start for a student who is working on machine learning and AI is to actually work on the field of shape memory alloys. So shape memory alloys are one of the foremost or one of the most easily available smart materials. There are various companies I know back in India also who actually sell these muscles or coils, I think, which I think students can just buy and then use. So shape memory alloy is something that you can start to work on, Bhumika, and you can actually use your machine learning skills to control that muscle.
And second question from my side, how could artificial muscle help in designing space robot that can fall, stretch, and survive extreme temperature variation?
Oh yeah, that's a that's a very good question. So NASA, I think, has used the artificial muscles in space also. So one of their space rover missions that was also using the shape memory alloys to make a reconfigurable wheel. So rather than using chains or metallic uh, components, they actually use shape memory alloys which can contract and then like expand when the temperatures change. So what happens is that Shape memory alloy is basically an alloy which is a composition of NITI, NITI. So that can change its shape and then retain its shape by so you can actually do it at different ranges of heat also by just changing the composition of Ni and Ti. So that is my answer to it.
Okay, thank you, sir. Any question from the faculty side? Dr. Sanjeev Sharma, Dr. Ravikant, Dr. Narendra.
Right.
So first,
Yes,
actually,
I
first of all, I
Hi,
appreciate
Dr. Sharma.
and for your insightful presentation. This is really wonderful.
Thank you.
I am very thankful to you because of number of student faculty members. Those are enriching their knowledges. So
Thank you, Dr.
actually there are 2 or 3 questions are there. Actually, you are really doing wonderful job. So as you know, as you actually stated that the jellyfish is having the maximum efficiency, it is very much correct. So various scientists are actually working in this direction. The reason is efficiency plays a very important and critical role, particularly for the seawater drones. Nowadays, seawater drones, those are very emerging field. A number of researchers are doing very well. So my question is, let us suppose because of it is also having a very less electrical or the magnetic signals. So any one is not actually detect where this particular type of drone is there. If jellyfish type of drone which you are doing which you are developing this particular drone, so it is a really wonderful job. So my question is, actually there are 2 things. One is endurance and second one is speed. So it's all right for the endurance because of the efficiency. Definitely endurance would be high. But once actually in this particular model, there is no any propellers and others. So speed, I think there is a speed is how you have to take the appropriate speed from this one. This is the first question. Second one is actually you are discussing about the coating of the graphene. Graphene, no doubt, there is a wonderful material, magic material, even we can say, because of it is having the highest thermal conductivity, highest electric conductivity, on all these things. So graphene powder you are using to dissipate the heat. Is it correct?
Yes.
Yeah.
So okay,
at the
sorry.
same
Please,
time,
please go on.
yes,
Yep.
yes. At the same time, if the thermal energy, or you can say heat, is going to be dissipated, at the same time, electrical current is also actually discharged. So what you should have to do for that one? And the third one is basically you are doing very good job because of nowadays I have seen one particular article that there is wing design is basically in UAVs. The wing design are made with the help of smart materials. So because of there are so many actuators are there, and because of the actuators and all these things, servo motors are there. Because of these all kind of things, the weight of that particular UAVs are too much. So we can change the angle of attack by just putting the current in that particular piezoelectric type of material. So these are the 3 questions. I think you are you could very much answerable for that one. So please.
Perfect. I think firstly, thank you for all the 3 questions. I think all the questions are valid. So let's begin. So firstly, you mentioned regarding the jellyfish speed or the jellyfish robot speed in water, right? So regarding that, as we are mimicking a real jellyfish, so the actuation frequency or the frequency speed of its flapping, so the wings flap for the jellyfish, So that range of flapping is between 0.1 hertz to 1 hertz. So when we are, so it's not always about speed. So when you want, say, a spy robot to be inside water, you don't want it to move fast all the time. So a jellyfish robot is trying to mimic every feature of a real jellyfish. A real jellyfish has an actuation frequency between 0.1 hertz to 1 hertz, which is like 1 second of flap. So one flap each second. But but in order to make it faster, you can actually use different artificial muscles which can be actuated at faster speeds also. So you can do that, but then you don't want to go there because your actual aim is to mimic a real jellyfish. So that is my first answer to you. Secondly, you mentioned regarding the material on the muscle. So basically graphene.
Yes.
Graphene is being used because what was happening was that one of the major defects or one of the major drawbacks of a twisted and coiled polymer muscle was that when it was being used in water, the heat which was provided to the muscle, it was being leaked out into the water. So in order to create a conductive layer which can retain the heat within the polymer, we wanted to have a conductive layer which does not leak the heat into the water also. So graphene was chosen as that material because the properties of that material allowed us to do that. There can be different carbon-based materials or nanomaterials like the carbon nanotubes used as that layer material also. But we use graphene because, as you mentioned, sir, the thermal conductivity properties or the properties of graphene are one of the best. So that was the reason. One more question connected to that was regarding the heat being leaked out. So when we are using the heating wire, let me maybe share my slide. I think I have one photo there. Okay, yeah. Let me share my screen. So are you able to see my slide? Okay. So
Yes,
this
yes,
is
Yes.
yeah. So this is something. This is the fishing line. This is the fishing line, the solid part. While this is the resistance wire, the heating wire. So what is happening is that we are not directly providing the voltage or the current to the fishing line, but we are providing the heat to the fishing line through this wire. And the nichrome, so this is a nichrome wire, NICR. The composition is NICR. That is why it's called nichrome. So this wire has a capability of retaining heat for a long time. So this is I think, this is your second answer.
yes.
If you can quickly repeat the last question.
So
I'm
the
very sorry.
last one, yes, yes, yes. Last one is basically, actually, I am asking about nowadays. You see, they are the UAVs
Yeah.
wings.
Oh yeah.
So
Yeah.
so nowadays, basically, such type of material they are developing to change the angle of attack, right?
Yeah.
So
Yeah.
otherwise, in general, nowadays actually there are number of actuators, servo motors are there. So all kind of things we are able to replace all kind of things by using this type of technology.
Yes.
So and we can achieve different kind of angle of attacks. so that
Yeah.
different lift would be there. So
Yes.
this is not
Yeah.
this is nothing a question, but just I want to update how actually the research or the area of your field is related to this. So
Yes.
could you able to discuss little bit more about the development regarding
Yeah.
this?
Oh, yeah.
Actually,
Surely. So,
sorry to
yeah.
interrupt, Dr.
Yes, Dr. Singh,
Sanjeev.
please.
We are
Yes.
running already too late.
Okay.
So it is better to wind up. Otherwise, discuss separately with, I will share with the contact and email ID, Dr. Pawan. Then you can
Oh
discuss
yes, yes, yes.
separately.
Okay.
That because of
Perfect.
our
Perfect.
session closed 11:30, right now 11:52. Sorry for interruption. That's the main thing. Thank you very
Perfect.
much for answering the questions. Now I will move forward session and hand over to the Dr. Ravikant Sharma for vote of thanks.
Yes. Am I audible?
Yes, yes.
Yeah, a very good afternoon to everyone. And on behalf of MIT University Haryana and the Department of Mechanical Engineering, MIT School of Engineering and Technology, it is my pleasure to propose the vote of thanks for today's international online expert talk on artificial muscles and soft robotics. First and foremost, I would like to express our heartful gratitude to our distinguished speaker, Dr. Pawandeep Singh Matharuji, for taking time out of his busy schedule to be with us today. Sir, your insightful talk, rich explanations, and real world perspective on artificial muscles and soft robotics have truly enlightened and inspired all of us. Your session has not only enhanced our understanding of this cutting edge area, but has also motivated our students and faculty to think about research, innovation, and practical applications in this field. We are deeply thankful to you for this. I extend my sincere thanks to our Honorable Vice Chancellor, Pro Vice Chancellor, Registrar Sir, Director Sir, for their constant encouragement and support in organizing such academic activities, events. I would also like to thank Dr. HRP Yadavji, Head Civil Engineering and Alternate Energy, for his constant motivation, academic leadership, and vision. Sir, your continuous support, encouragement have been instrumental in organizing such enriching expert talk and in promoting a strong culture of research and innovation among the faculty and students. My special thanks to our head of the department, Dr. Sanjeev Sharma, Mechanical Engineering, for providing continuous guidance and for motivating the department to conduct expert talks, workshops, and other scholarly activities on a regular basis. So I would also like to thank all the faculty members, staff of the Department of Mechanical Engineering, MIT School of Engineering and Technology, for their effort in planning, coordinating, and smoothly conducting this event. A big thank you to all our dear students, participants from MIT University, Haryana, and other institutions for joining this session with enthusiasm, maintaining discipline, actively engaging through your question and answers. Your participation makes these events truly meaningful. Last but not the least, I extend my gratitude to the technical support team for managing the online platform connectivity and coordination behind the scene to ensure that the session ran smoothly. Once again, on behalf of the entire organizing team, I thank each one of you for contributing to the session of this international online expert talk. Thank you. Thank you very much, sir.
Thank you, Dr. Ravikant. I request all of you participant and faculty members switch on camera for the group photo. Okay, thank you very much, sir. Thank you for giving the valuable time, Pawandeep sir. definitely when you come in India, so then
Thank you, Hardya.
I invite to you come physically in our university.
Thanks a lot. Surely, of course. Of course.
My congratulations to Mechanical Engineering Department for organizing this important talk. Thank you.
Thank you very much, sir. Thank you very much.
Thank you, Matharuji. Thank you.
Thank you, sir. Thank you. Thank you very much.
Thank you. Thanks a
Thank
lot,
you.
Dr. Shravan.
Thank you, sir.
Thank you. Thank you, guys. See you again then. Hopefully. Bye bye.
Oh,
See you guys.
bye bye, sir. Bye bye.